Hello, this is Mrs. Nearing, and we're going to walk through some notes on voltaic cells. So I apologize if the picture quality isn't great, but we'll do our best here. So this PowerPoint is also something you can find online as well. This unit's about electrochemistry, which has to do with the relationship between chemical and electrical energy, and electrochemistry involves redox reactions, and we've learned before that in redox reactions you're going to have two processes that are paired, an oxidation and a reduction. The oxidation process is going to involve losing electrons, and the reduction process is going to involve the gaining of electrons. And here's an example of a redox reaction in action. This is a classic single displacement reaction. So that's a good example of something you learned about in first year chemistry that now we can label as a redox reaction. So in this case, the solid zinc is being oxidized, so it's giving up some electrons to the copper ions. So the positive copper ions are turning into neutral copper. The neutral zinc is turning into positive zinc ions. So the thing being oxidized becomes more positive. The thing being reduced becomes more negative or less positive. An electrochemical cell is when you take a reaction like the one we just saw and you split it up into these two half cells. So we are separating out the substances rather than having them in the same beaker and connecting them through an external pathway such as a wire, and that allows us to trap that flow of electrons and turn it into something useful like an electric current. And there's two types of cells which you'll see. One's a galvanic cell, otherwise known as a voltaic cell, and this is what we use to make batteries. So this is with a spontaneous reaction. You hook it up, electrons are spontaneously going to start to flow. So that is a good source of electricity. Electrolytic cell is something that's non-spontaneous, and that is something that you can force to happen. Like you might hook up a power source to your electrolytic cell and make a reaction go, whereas this one's going to be spontaneous. And delta G equals negative NFE. This is an equation you will see, and so in order for a cell to be spontaneous, we know that for a process to be spontaneous, it has to have a negative delta G value. So in order for that to be true, it looks like it has to have a positive E value. And E is something we use to describe our cell. It's called the cell potential. And you may be familiar with the units of it. We describe that in terms of volts. So if you talk about something maybe a 10-volt battery, you're talking about the cell potential. Okay, so galvanic cells, otherwise known as voltaic cells, otherwise known as batteries. And these are devices that, again, separate those redox reactions into two separate half cells and allow the electrons to be transferred through a pathway such as a wire. So now you're creating a flow of electrons. That's electricity. So here's an example of it. You can see that the overall reaction looks like a single displacement reaction. Your zinc is being oxidized, so it's going from neutral solid to a positive ion. Your copper is being reduced, it's going from a positive ion to a neutral solid. And things that are involved in a voltaic cell, the kind of main components, is you have things called electrodes. Those are solid metals, conductive materials that are connected by the circuit, by the wire. On your electrodes you have two of them. One of them we call the anode, one we call the cathode. The anode is where oxidation occurs. Remember, oxidation is when you lose electrons, so that side of your cell is generating electrons. So often we label it as negative because that's where the electrons are coming from. And the cathode is where reduction occurs and electrons are flowing towards reduction. Remember, reduction takes electrons, so often we label that side positive. And a way to remember it is an-ox red cat. So reduction at the cathode, anode is oxidation. Then the metal electrodes are immersed in a solution containing the aqueous version of those ions. So for example, you will see that my solid copper is immersed in a copper ion solution. And notice I've got sulfate ions in there too, because in order to get copper ions, I have to dissolve an ionic compound. So I'm going to pick something something that would make my metal soluble, like maybe copper sulfate or copper nitrate or copper chloride. I wouldn't want to pick something like copper carbonate or copper phosphate because those would be insoluble. So I want something that would allow some copper ions to be dissolved in water as well as solid copper. Same thing over here, I've got solid zinc and zinc ions dissolved in water. And you'll also notice I have this thing called the salt bridge. This has some inert ions, so ions that are not going to interfere with the reaction going on. And this allows your solutions to maintain neutrality. So as these reactions occur, over here on this side, copper ions are being used up and turned into solid copper. That means this side of this half cell is becoming more negative because these positive ions are being used up. Now I'm going to have these sulfates hanging out there with no copper ions to neutralize their charge. So in order to keep this charge neutral, my cations in the salt bridge are going to move this way. So for every one copper plus 2 ion that leaves, 2 sodium ions will come over here and keep this solution neutral. On this side, I am generating positive ions. So to keep this side neutral, for every 1 zinc ion I produce, a sulfate ion is going to travel over here in order to keep this solution over there neutral. So the cations in the salt bridge are going to move over here towards your cathode because in that half cell, that's where my cations in solution are being used up. The anions are going to travel over here towards your anode because over here at the anode, that's where you're generating positive cations. And again, the goal is to keep the solution neutral. If charge starts to build up, so if you did not have a salt bridge, then electrons would stop flowing when charges start to build up in those solutions. So you've got oxidation occurring here that generates electrons that will flow through the wire over here to your cathode. The copper ions are going to grab up those electrons and become reduced, turning into solid copper. And then as this happens, my salt bridge completes the circuit, keeping these solutions neutral. So cations will travel one direction, anions will travel the other direction to keep these solutions neutral. So this goes through our voltaic cell components. And this is talking about the salt bridge. And then we'll do another video to talk about cell potential under standard conditions and non-standard conditions.